This is standing waves and interference, lesson number 7. And yesterday we talked about the principle of superposition and basically what happens when two waves meet and interact with each other at the same point in space and time. And so just to recall, if we say have wave A or a pulse A traveling this way, and we have wave B traveling this way, those two waves, or those two wave pulses, when they meet at the same spot in space and time, we add their amplitudes. And so we get this resultant pulse, which has a super trough and a super crest, and basically that's built each other up. Now, there's a special type of interaction between waves where we have waves that have the exact same frequency, this exact same wavelength, and the same speed. So really, they're identical waves, and they interfere with each other. That's a special type of wave, and we call it a standing wave. And here's an image of one right here where you've got a rope in between two fixed spots. And of course, this rope has been oscillated and is oscillating at a very specific frequency. And we get this standing wave pattern. And it's basically a system of nodes and antinodes so that we get interference where I've got one wave traveling from here down in this direction. I've got one wave traveling from here up in this direction, and of course these two waves overlap with each other and they build each other up. Now, this spot right here, which is a node, the string in this example wouldn't be moving at all, but here the string would have maximum movement. So let's talk about some of these specific details. A node is a region of a standing wave at which destructive interference occurs. So the waves are basically tearing each other down at this point. An antinode is regions in a standing wave that alternate between successive troughs and crests, and this is where constructive interference occurs. So the two waves have really built each other up here and really built each other up here. And the internodal distance is the distance between any two nodes. So here's a node here and here's a node here. And if we were to measure this distance using a ruler, we could find out the internodal distance. Now what we know about sine waves and cosine waves is that these won't change, right? The internodal distance between these two nodes and the internodal distance between this node and this node is of course exactly the same. This photograph is shot with perspective, so it looks a little bit different. But here, quick little video from YouTube. So this shows standing waves being set up on this string. And this goes on to show many different frequencies that give us standing waves. Now the interesting thing about standing waves and there's a different one. There's a different set of standing waves right here. The interesting thing about standing waves, here's yet another set of standing waves, is that there's only certain frequencies that will activate standing waves. Let's take a look at a quick example and then we'll get back to this idea of resonance. Whitewater Bay, which is the wave pool at Canada's Wonderland, uses a mechanism to generate large standing waves in the water. So if you see nodes every 1.8 meters and the speed of those waves is 2.50 meters per second, what's the wavelength and the frequency of the standing waves? So here's what we know. We know that the distance in between nodes is 1.8 meters. So that's actually the internodal distance. And we know that the speed of the waves is 2.5. I need to know lambda and I need to know frequency. And so here I introduce a little formula, which is that the internodal distance, the distance between any two nodes in any sine wave or any cosine wave, is just a half of a lambda. And so I can enter my 1.8 meters in for internodal distance, and this is going to directly help me calculate that the wavelength of these waves is 3.6 meters. If you have trouble visualizing this, just sketch out a little sine curve and say, okay, well, how much is a wavelength, and then how much is the distance between two nodes, and you'll see that it's exactly half. Now we can use V equals F lambda. We can substitute in. And we see right away that the frequency is 0.69 hertz, and that's the wavelength and the frequency of this setup. This is another example from YouTube of a river emptying out into a basin.
I don't know why I didn't think of this before.
And you see major waves here. But I want you to think about this. Are these considered standing waves? Yes or no, are they considered standing waves? And when you have an answer, we can discuss it in class. Here's example 2. A standing wave is produced by a source with a frequency of 30 hertz. It has a distance of 45 centimeters between 4 consecutive nodes. So we've measured and we've got 4 consecutive nodes and 45 centimeters in between them. So what is the wavelength and what's the speed of the wave? Well, as we go through here, we can say, okay, we know what the frequency is, and we know that 4 nodes in a row is 45 centimeters. So we better do a little sketch of this. And here's our 4 nodes, 1, 2, 3, 4. And I've basically drawn my wave. I've drawn my standing wave in between here. And I notice that 4 nodes gives us how many internodal distances? Well, there's 1 here, there's 2 here, and there's 3 here. So I have this 45 centimeters, and it's divided by 3 different internodal distances. So each one of these internodal distances is 15 centimeters. So 0.15. Oh, excuse me, 0.15 meters. So 15 centimeters. And so now I need to find lambda and I need to find the wave velocity. So let's look at lambda first. You would probably notice that this is 1 full wavelength, and of course an internodal distance is just half of this 1 full wavelength. So if you had trouble visualizing this before, we can look in here. And I get 0.15 is equal to a half lambda. My wavelength is equal to 0.3 meters. Now I can use the universal wave equation, V equals F lambda. I know what the frequency is. It was given to me in the problem. I now have the wavelength, and I can solve and say that this wave is moving at 9 meters per second. All right, moving on. Let's talk about interference and maybe more general cases of interference, because when waves interfere, they don't have to be standing waves. They don't have to interfere in a way that basically creates standing waves. They can interfere in all different kinds of cases. So we're going to examine a lot of these different situations, but let's think about when interference might occur. Any 2 waves represented by their corresponding sine waves, right? So let's select, here's 1 wave right here, okay? And we'll select another wave that's basically just phase shifted or 1 full wavelength longer than this wave. So these, of course, would be continuous. They'd continue down here and they'd continue up here. Same with this. This one would continue over here and would continue back here. But if they're 1 full wavelength different in their phase, what kind of interference do you see if you were to add these 2? They're perfectly over top of each other. If you were to add their amplitudes, you of course see constructive interference. So they would add to build each other up. Now, in contrast to this, let's consider 2 waves that are off not by a full lambda, but by 1/2 of a wavelength. So here's one of the waves, and here's the other wave. So now these are off by, you can see the phase difference here. One is just shifted by about 1/2 of a wavelength. And if I was to add up this amplitude, this amplitude, this amplitude, this amplitude, and I was to go down and I was to add up all of these amplitudes, of course, what do these waves do? They cancel each other out. So this is completely destructive interference. They subtract each other and basically level each other out, so we've got 0. And so these are our 2 cases, or our 2 conditions for perfectly constructive and perfectly destructive interference, and here they are. When I have constructive interference, it means 2 waves are interacting that have a difference or that have a shift of a full number of wavelengths. So one wave could be off by 2 lambda, the waves could be off by 3 lambda. As long as they are off by a full measure of a wavelength, they're going to interfere constructively. Destructive interference is basically when any waves are off by any half integer number of wavelengths. So these two waves could be off by 3.5 wavelengths, 4.5 wavelengths, whatever. As long as there's this factor of a half in there, they interfere completely destructively. And these are two very important conditions. All right, as we move along, this is a cute little video. You can find this on YouTube. This is called Rice resonance. And this shows, as they go through different frequencies, different patterns of standing waves that are formed in a two-dimensional surface. And there's all kinds of different patterns that you could go to and that you should go and really take a look at this. Rice resonance is what it's called. It's on YouTube. There's lots of different special cases of where interference can be observed. That was one of them. They're all well explained in your textbook. A Herschel tube is this special device that adjusts the length of the path that sound has to travel. And so it changes the number of wavelengths between one path and another. Two speakers, we're going to do this one in class today, two speakers side by side will produce constructive and destructive interference. Beat frequency, we'll also do this in class today, is that a special kind of interference when two notes are very close in frequency. So here's two that haven't been shifted by a lot, and you can see that they haven't been shifted by a lot. They've just been wavelength, like the wavelength is just off by a teeny tiny little bit. But what happens when those two things are added together is you get this very complicated waveform. And you kind of hear this as a beat. Bow, 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 bow. And so that's what a beat frequency looks like. And here's the result of the combination between the two of these things. This is a little bit complicated, but this is from your textbook. But in order to find that beat frequency, you simply take the frequency of one and you subtract the frequency of the other, and you end up with this beat. And we're going to look at that today in class. You can also do a quick little YouTube search for beat frequency, and you'll find exactly what this sounds like. It's probably more familiar than you realize right now.